look at implementing the SIS model in Excel, so we can do simulations and actually look at the long-term behaviour of this particular difference equation. So to do this, we start by opening up Excel, and what I'm going to do is in cell B1 I'm going to write the word kappa. That will be our variable kappa. And in D1 I'm going to enter the word beta. And in cell 1 I'm going to write, in cell F1 I'm going to write kappa divided by beta. So all this is just text. Now for our simulations, this cell here, C1, will contain the numerical value of kappa, E1 will contain the numerical value of beta, and G1, well, that's actually going to be the formula that, if you remember, gave us the steady state, i.e. the long-term behaviour, kappa divided by beta. So I enter the formula equals C1 divided by E1, and I hit return. In the moment, it's going to return me an error message. The reason is because there's nothing to divide. So let's start by entering the values 1 and 2, and that will give us 0.5. Now we're going to start by, in cell A3, we're going to enter T, so that represents our time period. We're going to have I of T in B3, and we're going to have S of T in C3. So I want to enter the numerical value 0 in A4, that's because the time period is going to start at 0. Now, this cell here contains the formula for how to get IT at a particular time period. Now, I'm going to start and suppose that I've got 0.1, well, that's the proportion of the population that's initially infected. Now, if we go back to our original piece here, we can see that S is always given by 1 minus the value that I currently is. So that's because we assume that the total population adds up to 1. So this is going to be 1 take away this value here. Now, we then want to actually move on to work out the next time period. So I'm going to have the formula in here being the previous one plus 1. Our time period is going to go up in jumps of 1. Now we want to work out the formula that should go in here. So this is the number of infected at the next time period. Now if we look at the formula, the number of infected at the next time period is the value of beta times 1 minus the previous value times the previous value. So that's exactly the thing that I'm going to enter in here. So it's going to be equal to the value of beta. Now, because I'm going to copy these formula, I'm going to put dollar signs around it. And what that means is, when I try and copy this formula down, it will always, that particular part of the formula will always refer to that cell there. Times 1 take away the previous value times the previous value. So that's the formula that we've now got. So if I press return, Excel has worked out for me the value of the infected at the next time period. Now, for cell C5, I can just copy the formula down, and that now does 1 minus B5, i.e. it's correctly calculating the number of susceptibles. Now what I can do is I can select these here, and I can now drag, by selecting this thing down here, to get about 30 simulations. And if you notice, you can see here the number of infected and the number of susceptible have eventually and quite quickly reached the value of 0.5, which is exactly what we suspect we should get given the previous analysis we did during the lecture. So now what I want to do is I actually want to draw a graph of this. So I select all my data that I have here. I go to the chart wizard here. I select the XY scatter graph and I select to join it up without the dots. And you can see there that we get a very quick version of the graph. So I hit finish and that gives me a exact copy of the particular graph. So now what we can do is we can investigate what happens as we change this value of beta. So we can make it 2.5 and we can see how the values now separate out. If you want to make the lines thicker, you can double click on them to make them larger, and it's now your task to investigate what happens as you change this value of beta here.